Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture, I'll be talking about absorption in tray column. So far we looked at absorption in a packed column. A packed column is one where we have a packing of inert material to allow a continuous contact between liquid and the gas. There's an alternative equipment used for absorption, and that is a tray column. Okay, so let me show you how this tray column. So this is a kind of a schematic of a tray column. It is basically a tall vertical tower. The gas goes in here at the bottom of the tower and then leaves at the top, very similar to packed bed column. Similarly, liquid actually enters at the top and then leaves at the bottom. Okay, so in terms of the input, output and flow conditions, they are very similar to packed column overall considered. But then what is the difference between the tray column and the packed column is that what is there inside the column. In this particular operating equipment, the column is fitted with many trays. These are called sieve trays, for example. Okay, so you can see that there is a tray here with perforation, and you can see there are many of them stacked at certain interspacing between the tray. So what happens is that this gas will go through these trays upward. So once the gas enters, they enter through this perforation of the tray and move upward. Okay, so these are the provisions for the gas to flow through. Whereas the liquid enters from the top, it kinds of has a particular height of liquid column and then overflows from the side of the tray through a down port or a downcomer. So you can see this enters here, flows across the column, and then from the other side it flows down and then fills the next tray, and then from here it goes to the third tray. So you can see that this liquid follows more like a zigzag kind of a path, filling from one tray to the other subsequently. Okay, so now the incoming gas will have to go through this liquid, okay, through bubbles, and this is where the actual contact between the gas and liquid happens. Okay, so you'll have in each tray there will be a column of liquid through which the gas will bubble through, and because of this bubble dynamics, bubble will form, it will coalesce, and then through the interface between the gas and liquid, the mass transfer will take place. Here there is no packing. The interface contact between the liquid and the gas is provided through these bubbles. Okay, gas bubbles going through the column of liquid. So this is a kind of very generic schematic that shows the flow pattern of a gas and liquid in a tray column. So let me also show you a little bit about how the trays are made and what is the. So there are many kinds of tray. So this is called this sieve tray. Yeah. So this is called the sieve tray. You can see there's a perforation which is present in this tray. So this is where the gas will go through. Okay, and just above this tray there will be a column of liquid, and the bubble will have to go through this column of liquid in terms of bubbles. This is one possibility. The other possibility is called bubble cap tray. Here there is a perforation, but above the perforation there is a cap. Okay, so if I draw the cross section of this, you will see that it has a cap like this. So I am showing one particular perforation. The gas will have to go through and then take this kind of a path. So this kind of allows good control of bubble formation and then transport. Okay, so you see that there are many other kinds of tray, but predominantly used trays are the sieve tray and bubble cap tray. These allow transport of gas from one tray to the other. Okay, and so that is this is about the structure of this particular tray column. And next is about the operating conditions. When we talked about packet column, I said depending upon the flow rate of the gas and the liquid, you have different flow regimes. Okay, there is a flooding, and there is trickling, and pressure drop is very much proportional to the flow rates of the both gases and the liquid. Similarly, in this case also, because this liquid and gas will have to go through multiple trays, the pressure drop also will depend on the gas and liquid flow rates. So the flow regimes can be shown by this schematic. In fact, the flow regimes are pretty complex in tray column compared to packet column. So you'll see that I'm looking at so on the y-axis vapor flow rate is mentioned, and the x-axis we have liquid flow rate, and then we are looking at different possible flow pattern in the tray column. So you see that when the vapor flow rate or liquid flow rate are very high, we find this column floods. The flooding is very similar to the flooding in packet column, where the column will be completely filled with the liquid, and then the operation is not stable. Okay, and we don't want to operate the column under flooding conditions. Okay, a stable operation is the zone which is shown as spray, froth, and emulsion. Okay, these are the regimes where the column can be operated. So in spray, what happens is that you have a very high gas flow rate and a very small liquid flow rate. In this case, what happens is this is a spray regime, where the incoming gas will actually make sprays out of the liquid. Okay, so you'll see there's a liquid is going like a spray. So this is a photograph taken in situ of a column operated under spray conditions. Okay, another one is emulsion. In the emulsion regime, you see that bubbles. So here, what is shown here is the perforation, and you can see the formation of bubbles here. The bubbles are formed, pinched off, and small bubbles basically go through this column of liquid. Okay, so we call it as emulsion because it is a two-phase flow. It has a gas bubble flowing through a column of liquid. Okay, this is called emulsion regime. And there is a froth regime. In froth regime also we have gas bubble, but here gas bubble form, coalesce, and they form in different sizes and different shapes, and then it flow through this column. So this is called froth regime. So the column can be operated in any of these three. Okay, but you don't want to go to flooding, and you don't want to go to this very low flow rates. Okay, so when you have very low flow rates, like gas is very small and liquid is very high, then this is called the bubble regime, and that is not very optimal. And another thing is, sometimes when you go here at a very high, even higher flow rates, you might have what is called this entrainment. So in entrainment, what happens is the liquid gets carried over in the gas stream itself. When the gas goes out of the column, it carries some of the liquid with it. That's called entrainment, and that is also not something we should be operating on. So the safest place to operate is either spray or froth or in emulsion regime. In terms of design principle, what we would like to do is, when we have a column like this, we are generally interested in finding out, for a given set of liquid and gas flow rates and the composition change, how many plates, how many trays I have to provide. In the case of packet column, the design question was how high the packing should be, which we dealt with calculating the height transfer unit and number transfer unit. In the tray column, here we are interested in the number of trays. Okay, and the trays are placed with a particular distance, allowing that at sometimes you want to go in and then clean this tray. So the tray spacing is considered based on other mechanical and maintenance purposes. But here the design principle is to calculate how many trays. Once you know the trays and then fix the tray spacing depending upon these other requirements, then you know what is the height of the column is. Okay, so in this tray column design, The question we are trying to answer is what is the number of trays that we need to provide. Okay, not really the height of the column per se. Now this calculation can be again done by two possibilities. One is a graphical method, another one is an analytical method. Okay, so in terms of a graphical method, so we can show this a column in this particular schematic. So you can see that so here is a schematic. What you see here is that so gas is coming in here. Okay, this is gas in and this is gas out, and here liquid is in and then here it goes out. The way we have numbered this column is slightly different from how we numbered this packet column. In the packet column, this suffix 1, y1, x1 was denoted at the bottom of the column, x2, y2 are denoted at the top of the column. Okay, because we assumed that the entire packet column is like a one stage. What is a stage? A stage is a piece of the equipment where the two fluids are mixed, allowed to happen mass transfer, and then we separate the fluids. That's called one stage. In the packet column, the contact is continuous from the bottom to the top. The two fluids actually separate only at the top of the column. So the entire column is like one stage. But in this problem, since we have this tray, at each tray, the two fluids mix, mass transfer happens, and then they separate also. They separate because there's a density difference between the two. The column is otherwise hollow, so they can actually phase separate and then go to the next column, mix again, and then mass transfer happens, and again they separate. So this is like more like a stage-wise operation. It's continuous within a column, within a tray, but then between the tray, this is like a stage-wise operation. Fluids are mixed, mass transfer happens, fluids are separated, and this gets over and over as the fluid goes through the column from the top to the bottom. Okay, so that is the main difference between the tray column and the packet column. It differs in the way in which the two fluids are contacted. Okay, in one case, packet column, it's continuous contact. In the tray column, it is a stage-wise contact. Okay, so here the numbers of the tray come from the top. This is the first tray, second tray, third tray, and then to show the column, there is we are showing this by a breakup, and then there is a total of NP number of trays. P means plates. Okay, either trays or plates. Number of plates or number of trays. So the trays are numbered from top to bottom. Okay, and because of that, the gas streams and the liquid streams are also numbered such a way that the outgoing gas composition is given by y1 and the incoming liquid composition is given as x0. So this is slightly different from how we used the nomenclature in the case of packet column. So I want you to take note of this difference. Okay, and the reason why we do this way is because when we deal with this packet column and the design is to calculate the number of trays. Okay, so now here we would like to say that in each tray the outgoing streams are at equilibrium. So that's an assumption that we're going to make. This basically leads us to define ideal tray or ideal stage, where the outgoing fluids are in equilibrium. So what do I mean by that? If I look at the first tray and you see this y1 is the composition of the gas leaving this tray, x1 is the composition of the liquid leaving the first tray. With respect to the first tray, the two streams which are leaving are numbered with suffix 1. Similarly, if I go to tray 2, the two streams that are leaving are y2 and x2. So the numbers are done such a way that that streams leaving a particular tray are given the index of that particular tray. The streams that are leaving the first tray are denoted with x1, y1. The streams that are leaving tray 2 are x2 and y2, and so on, and so on. So, and because of that, when you go to the NP tray, the last tray, the outgoing composition of the liquid is xnp, and the gas is YNP. Okay, and because YNP is used for the outgoing, the incoming will have to be NP plus 1. So that's the reason why we have used a little bit of a different way of nomenclature here. Okay, because we want to give the same index for the fluids leaving a particular tray, x1 y1, x2 y2, x3 y3. Okay, and now when I say the outgoing fluids are in equilibrium for an ideal tray or a theoretical stage or ideal stage, you will see this two, x1 and y1, will be at equilibrium. Similarly, the x2 and y2 will be in equilibrium. What that means is, when the two fluids are made into contact in a particular tray, there is enough time available for the gas and liquid to mix, so that the mass transfer comes to completion. Okay, all the so basically the streams are at reaching equilibrium concentration, so there is no further mass transfer, so they separate, go to the next stage. Okay, and then another level of mass transfer happen in another stage. So we see that in each stage, when the fluids are leaving the stage, they are at equilibrium. So that is something that we assume, and we call those as ideal trays or theoretical stage or ideal stage. Okay, these are synonyms. Now, having defined this ideal stage, what we can do is we can calculate the number of stages or number of ideal trays. Okay, this can be done by either graphically or analytically. Okay, in some cases at least. So for example, what you see here is y versus x in terms of mole ratio. So this line that you see here is this is the equilibrium line, and this is the operating line. So the equilibrium line comes from the thermodynamics, operating line comes from the mole balance equation. Okay, so now because we have changed the notation here, if you look at the composition at the top of the column, what is the composition of the two fluids at the top of the column? X0 and Y1. Okay, the streams that are coming in and going out at the top of the column is X0 and Y1, right? And that is actually denoted here. That is the top of the column. And if you look at the bottom of the column, because of the way that I talked about how we want to number this fluid streams, at the bottom you have XNP and YNP plus 1. So that is this point, YNP plus 1 and XNP. Okay, so this basically denotes the bottom of the column, and this is the top. Okay, so now we want to calculate the number of theoretical stages or number of theoretical plates, whatever that you call. Okay, so the way we can do that is, if you go to the first tray, and you can see that what is leaving is x1 y1. So that is this x1 and y1 are in equilibrium. You can identify that in the equilibrium line. Okay, and then y2 x1. So maybe I can if I take let's say if I take stage 1 here, so the gas that is coming in is y2, and the liquid that is leaving the stage is x1, right? So that is the point that I can note here. So the fluids that is coming into the first stage and the fluids that are leaving the first stage are basically this entire step, right? And it also such a way that the two outgoing streams x1 y1 are at equilibrium. So this particular step that I am talking about is the first stage, theoretical stage or ideal stage. Now if you similarly go to the second stage, and you see that what is coming in is y3 and what is leaving is x2. So that is this point. Okay, and also such that the x2 and y2 are at equilibrium, and we call this is the second stage. And then similarly, if you go further to the third tray, you will see that y4 and x3 are the outgoing streams, and then x3, y3 are at equilibrium. So you can easily construct this kind of a staircase diagram between these two, operating line and the equilibrium line. Okay, so start from here, reach horizontally to the equilibrium line, and then go up and meet the operating line, that is equilibrium stage 1. Then from here you go horizontally to the equilibrium line, because we are assuming that the outgoing streams are at equilibrium, because this is a theoretical stage or ideal stage, and then go upwards and meet the operating line, that is number stage 2, and then you continue this operation, and then when you go to the top of the top of this line, the composition corresponding to the bottom, that would be your NP. So this method is very simple. All you need to know is what is the equilibrium line, what is the operating line, which you can get by doing mole balance, and then you can do this staircase construction to get the number of equilibrium stages. Because like I said, what we are saying is that the design is such a way that if you go back here, the actual design has this provisions that will maintain a particular liquid column in each tray. Okay, you can see there is a leveling here, so as to let the only overflowing liquid out. So there is a small wire here that will keep a particular column height, liquid height maintained. What that means is we are allowing a particular volume of liquid to be always there at a steady state, so that the incoming gas can interact with. Okay, so this will take care of the equilibrium, approach to equilibrium. Okay, but in reality this will not happen, but here we are assuming that there is enough provision in each stage such a way that the mass transfer comes to completion in each stage. Therefore, the gas that is leaving and the liquid that is leaving a particular stage are at equilibrium. Okay, now the interspacing with the tray depends on several things. For example, depending upon the nature of the tray, it has to be cleaned once in a while. Okay, so there should be a provision so a man can actually enter this column and do the cleaning operation and come out. Okay, so the sieve spacing is decided by other consideration other than mass transfer, about maintenance, cleaning and various other things. Okay, but from a mass transfer point of view, we are interested in, if I assume that each stage allows equilibrium to reach, how many number of such stages I have to provide? That's the question that we can answer through mass transfer, and that's exactly what we are doing here. Okay, you can also correlate what we did in the last class about packed column design using graphical method, where we never did this. We never reached to the equilibrium line, because there we didn't assume that there's no stage there, and we can't say that two fluids are at equilibrium at any given point. So there it is a continuous contact. The graphical method is slightly different, but here the advantage of this method is that it allows us to do this nice construction of staircase, because we can assume ideal stage at each stage. So the way we will do this is, for a given problem we will calculate the number of ideal stages. There is a second aspect which is related to the efficiency of each tray. Here we assume 100% efficiency. Okay, but in reality that is not the case. The efficiency can be 50%, efficiency can be 60% or 80%, whatever it is. So there is an independent calculation about tray efficiency. Once I know the tray efficiency and I know the ideal number of stages, I can calculate the actual number of stages. Okay, so that comes later. Right now we are focusing on calculating the number of theoretical stages or number of theoretical plates or ideal number of plates. It's all synonyms. Okay, and this is very easy to do, because I can start from the composition, reach the equilibrium line and go up and then continue with this, because I am assuming each stage is equilibrium. The next thing is, when we did this graphical approach, the only assumption we are making here is that the stages are ideal. We are not saying anything about whether the equilibrium line should be straight line or operating line should be straight line. Okay, but if the if the compositions are very small, and if the operating line and the equilibrium lines are straight line, then we can get an analytical solution for this problem. That is, I can calculate the number of ideal stages from an analytical expression. Okay, if the three conditions, dilute mixtures, the equilibrium line is a straight line and operating line is a straight line. So in that case I can use analytical solution. Okay, so that's what I'm going to demonstrate now. So NP is the number of theoretical stages, or you could say number of ideal trace. So the same figure that I showed before. So what the assumptions are, dilute mixtures, so that I can write G1 is almost equal to GNP plus 1 almost equal to GS. Similarly, the liquid flow rates are almost constant. And third is that I can write Y star is equal to mx. Okay, so if you make these assumptions, then we can set out a analytical solution for the calculation of number of theoretical stages. So first what we will do a mole balance on the last tray, which is the NPth tray. Okay, so the NPth tray is this, the last tray here. So you can see that if I look at the last tray, so I can draw here, this is the NPth tray. What comes in is YNP plus 1, and then what leaves. So you have to imagine that there is a small liquid column here, so that the mass transfer can happen. And then if you look at the composition of the outgoing gas here, that would be YNP. Similarly, in this tray, the liquid that is coming in has a composition of NP minus 1, and the one that leaves is XNP, such that these two are at equilibrium. The two outgoing streams XNP, YNP are at equilibrium. So for this I have written a mass balance. So if you see what is the number of moles of the solute coming in would be G times this mole fraction, and the number of moles in the liquid stream that is coming in would be L times XNP minus 1, and that should be equal to the number of moles that is leaving, that is this stream, plus the liquid stream that is here. So here I have used G and L as constants. Okay. So now what we can do, I already said that the XNP and YNP are in equilibrium. So that means they are related by the equilibrium line. So that means this YNP will be M times XNP, because it's an ideal stage. The outgoing streams are at equilibrium. Okay, so I can remove one variable from here. Okay, I can replace XNP with respect to YNP. And similarly, I can also replace XNP minus 1 with YNP minus 1. So remember this YNP1 is actually coming from the previous tray, that is NP minus 1 of the tray, and that should be at equilibrium with the previous tray's outgoing stream. So both XNP and XNP minus 1 are in equilibrium with those corresponding gas streams that are leaving each tray. Okay, so this would be the case. So if I look at this NP minus 1 tray, you can see that this X NP minus 1 and this Y NP minus 1, they are in at equilibrium. So I can relate them through this equilibrium relationship. Okay, so therefore in this particular mass balance at the npth tray, I can replace both the liquid phase compositions using gas phase composition because I know that they are in equilibrium. Okay, so this gives me Y times YNP plus 1 plus X times YNP minus 1 by M, that is equal to G times YNP plus L times YNP by M. Okay, so all we are trying to do is I am replacing all the liquid phase compositions with respect to the corresponding equilibrium gas phase composition. So we can do a little bit of rearrangement here. So you can see this factor L by mg comes out, and we know it is an absorption factor. So there are two terms on NP, so I can write YNP times 1 plus A, that is equal to YNP plus 1 plus YNP minus 1. So therefore YNP is equal to YNP plus 1 plus YNP minus 1 by 1 plus A. Please check if there is an what is it? A times, okay, so that should be here, right? Okay, yeah, thanks. Is it right? YNP plus 1 plus A times YNP minus 1 by A plus 1. Yes, this is something we have written for the last tray, and you can see that this is related to the concentration of the NP plus 1 and the previous tray NP minus 1. It's kind of a recursive relation. The composition at each tray can be related to the composition of the tray above and tray below. Okay, just to see that, if you want to look at let's say if you want to put NP equal to 1, or you can say for the first tray, so you will see that Y1 is equal to Y2 plus A Y0 by 1 plus A. Okay, if I substitute for NP equal to 1, I will get this. But the problem is, if you look at this graph, we don't have anything called Y0. The smallest is Y1, that is the outgoing stream. Okay, so what does Y0 means here? Y0 basically means X0 is defined. Okay, imagine there is a virtual tray, 0th tray, from which X0 and Y0 are actually at equilibrium. You can imagine Y0 is an equilibrium composition of a fictitious tray corresponding to the composition X0. Okay, but for now Y0 is nothing but M times X0. Okay, so that's what this means. And then if you look at second tray, so you can say y2 is equal to y3 plus a y2 by 1 plus a. A y1, yes, this must be a y1. So the composition at the second tray y2 is the one that leaves the second tray, is related to y3 and y1 through this absorption factor. Now, but I already know how to write y1 in terms of y2 and y0. So in principle, I can actually replace y1 from here. Okay, so if I do that, I'll just give the expression, but you can check this out. You will see that y3 into 1 plus a square y naught by 1 plus a square. So y2 now depends only on y3 and the y naught which is known for us. And then suppose let's say I do for third tray. So y3 will be y4 plus a times y2 by 1 plus a from the recursive relation. But now I already know what is y2 in terms of y3 and y0. Okay, so I can now substitute that and I can start basically building this recursive relation subsequently. And if I continue to do this, I can write ynp. I'll give the final result. Ynp can be written as ynp plus 1 a absorption factor to the power np minus 1 plus a to the power np into a minus 1 y0 by a np plus 1 minus 1. So this basically comes merely from the mole balance that we have done, okay, and also making sure that they are in equilibrium, the outgoing streams are in equilibrium. So in principle, I can use this expression to calculate NP. Okay, what are the things I know to calculate NP? What are the things that I know and what are the things I don't know? Do I know x, y naught? Yes, because it's m times x naught. X naught is known, it's the inlet concentration of the liquid. What about absorption factor? I know. What about ynp plus 1? I know. ynp? ynp I don't know, because ynp is the so if you go back to the schematic, ynp is the composition of the gas leaving the last tray. This is not accessible for us. I mean, of course you can measure if you want, but theoretically what we know is only the inlet outlet compositions, absorption factors also, but we don't know ynp. Okay, so what we want to do is, I want to deal with this. If I can, there are two unknowns in this problem. One is np, which I want to calculate, and ynp, which I don't know. So I want to calculate this. Okay, so the way forward would be, we can do another mass balance over the entire column. If I look at the entire column, the inlet outlet streams of the gas and liquid, I can set out one material balance equation, and that will be one additional equation I can use to replace one of this variable here. Okay, in principle I can replace ynp from the overall mass balance, then I will get an expression that will involve only one unknown, which is np. Okay, so mole balance on the entire column. When I say entire column, I am just talking about the inlet outlet of the entire column. Okay, so you will see this becomes g times ynp plus 1 minus y1, that should be equal to x times xnp minus x naught. And like before, we will replace this with equilibrium line. as YNP by M minus Y naught by M. So you can see that I have another equation that relates YNP and YNP plus 1, and I have another equation here also relating YNP and YNP plus 1. From these two equations I can eliminate YNP, which is an unknown. Okay, what that means is I can substitute for this expression YNP in here, right? Then I can solve for this equation, and again this some arithmetic you have to do, algebra you have to do here. So the final expression that you will get by solving would be log of So you can see this final expression solves for the unknown number of theoretical plates using all the known variables: inlet compositions, absorption factor, okay, which involves the slope of the material operating line and the equilibrium line, and this is known as a Krasmer equation. Krasmer's equation for absorption. So this entire analysis you can do for stripping also, and you can get an equivalent expression for stripping as well. So that goes as the following. So where S is equal to 1 by A, it's known as stripping factor. So this Krasmer equation is very important because from if you look at gate questions on absorption at a tray column, pretty much entire questions actually come in this application of this equation, because it's an analytical result. Very rarely you get a graphical questions, okay, and it's not that you have to memorize this. Generally these equations are actually given. You have to know how to use this equation, that's all. Sometimes this absorption factor A may not be given, that's something you have to calculate, okay. Otherwise pretty much it's more like a substitution and get the answer. In some form you will see this equation has some resemblance to the similar equation we derived for packed column for dilute mixtures, okay. So this factor 1 by 1 minus A plus 1 by A, it was also there, and I think the denominator had a 1 by 1 minus A factor, okay. It's slightly different, mainly because of the nature of the operations are different, okay, continuous versus stage. Yeah, so that's all for today. So yeah, if you have any questions, so you can ask. So by the way, this completes the discussion on absorption, okay. Well, not really. There's one thing I want to talk about, that is efficiencies, okay. Once we get the efficiency, we get the number of theoretical plate from here, and then we get efficiency independently, and from there we can count the number of real trays.